A transparent chemical reactor begins with a large borosilicate glass vessel blank. This material is chosen because it resists corrosive chemicals, tolerates rapid temperature changes, and allows operators to observe reactions directly. The vessel continues rotating, while powerful flames raise the rim to an orange working temperature. At this stage, the normally rigid glass becomes soft enough to reshape. Workers use heat-resistant tools to control the opening and maintain a uniform wall thickness. The temperature must remain balanced around the circumference. A section that cools too quickly could contract unevenly, creating hidden stress or small cracks inside the future reactor. A separate glass tube is heated at the same time as a prepared opening on the vessel. Once both surfaces soften, the worker presses them together to form a new process connection. Accurate alignment is essential because this nozzle may later carry sensors, pipes, or circulating fluid. Workers continue rotating the vessel while applying heat to the flange and surrounding wall. Local torches correct small areas without reheating the complete glass body unnecessarily. The softened rim is gradually widened, rounded, and polished. Slow, controlled shaping preserves the glass thickness around the opening. Removing or stretching too much material could create a weak section where clamps and internal pressure will later apply force. A separate domed glass lid is prepared for its smaller process ports. The worker heats both the lid surface and a short glass neck until their edges become soft. The two pieces are fused while a graphite rod supports the opening. This tool prevents the hot neck from collapsing and keeps its internal diameter round. A smooth bore is necessary for correctly fitting seals, thermometers, feed tubes, and laboratory accessories. Additional glass nozzles are attached around the lid using the same controlled flame-working technique. Each connection is positioned for a different reactor function. Workers repeatedly heat, fuse, shape, and flame polish every joint. Port spacing is carefully planned so valves, condensers, vacuum lines, and sensors can operate without interfering with one another. Uniform joints also distribute mechanical and thermal stress more safely through the glass. The assembly team installs the bottom drain valve, sealing components, clamps, and central stirring system. Many contact parts use chemically resistant materials such as PTFE and stainless steel. Every fitting is tightened carefully by hand. Excessive or uneven force could crack the glass flange. The electric stirrer drive is aligned directly above the vessel, so the long shaft can rotate without striking the reactor wall. Through precise flame heating, skilled glass forming, careful assembly, and controlled testing, a glass vessel has become a fully functional chemical reactor. A hand-built wooden boat begins with long, straight timber planks selected for consistent grain and minimal cracking. The craftsmen arrange the boards on level supports and mark the required center lines and joining points. Small holes are prepared along the edges before wooden dowels are inserted. These pegs keep neighboring planks aligned and strengthen the joint without concentrating stress around large metal fasteners. The long side boards are raised and positioned against the developing bottom structure. Several workers hold the heavy timber in shape, while another secures it with nails and temporary supports. Portable planers smooth the meeting edges and correct small differences in height. The bow and stern sections are drawn inward to create the boat's tapered profile. Workers measure across the hull repeatedly so both sides curve symmetrically. Pilot holes are drilled before screws or nails are installed. Pre-drilling reduces the risk of splitting near the plank edges, while careful fastening keeps the timber firmly positioned without crushing its fibers. Individual floor frames and transverse ribs are measured, cut, and fitted between the sidewalls. These members determine the boat's width and support the curved hull shape. Each frame must contact both sides evenly. Poorly fitted ribs could twist the hull or concentrate loads in one area when passengers, cargo, and engine weight are added. Circular saws, planers, and abrasive tools remove projecting edges from the assembled hull. The craftsmen repeatedly sight along the boat to identify bumps, flat areas, and uneven curves. This process is known as fairing. A smooth exterior reduces drag in the water, while balanced shaping prevents the finished boat from pulling toward one side. Long internal stringers and upper rails are fitted along both sides of the boat. These continuous wooden members connect the individual frames and increase stiffness along the hull's full length. Workers trim every joint carefully before fastening. The upper rails also reinforce the open edge, which must withstand lifting, docking impacts, and repeated movement from passengers. Wide boards are measured and cut into gunwales, floor panels, and other finishing components. Workers use portable saws to follow the boat's changing outline before refining the edges by hand. Every piece is test-fitted before permanent attachment. Accurate cutting minimizes gaps and preserves valuable timber while keeping the boat's weight evenly distributed. The exterior receives a protective coating to reduce moisture absorption and slow deterioration of the wooden surface. A compact engine and long propeller shaft are then mounted across the reinforced stern structure. Workers check the supports and shaft alignment before operation. Through careful joinery, precise shaping, and skilled hand assembly, raw timber has become a practical motorized wooden boat. A large water storage tank begins with powdered polyethylene resin, chosen for its corrosion resistance, low weight, and ability to form a seamless waterproof body. Workers measure the resin and blend it with stabilizers and orange color pigment. The fine powder must remain evenly mixed because inconsistent material distribution could create weak areas or visible color differences after heating. The prepared polyethylene powder is transferred into a large split metal mold through its central loading port. Workers distribute the measured charge before closing the heavy cover and securing every clamp. Accurate dosing controls the tank's final wall thickness. Too little resin would produce thin sections, while excessive material would add unnecessary weight and increase heating time. Rows of powerful gas burners heat the outside of the mold while the machine rotates it through multiple directions. As the temperature rises, the polyethylene powder melts and gradually coats the entire internal surface. Continuous rotation is essential because gravity alone would collect the plastic at the bottom. Controlled movement creates a hollow tank with more uniform walls. After heating, the mold is cooled until the plastic becomes rigid enough to retain its shape. Workers release the clamps and separate the heavy mold sections. A lifting device helps remove the large orange tank without twisting it. The newly molded body is inspected for uneven thickness, surface defects, and deformation before additional structural work begins. Large steel sheets are measured and cut into long strips using powerful thermal cutting equipment. Workers then bend the strips into curved reinforcement ribs matching the tank's diameter. Although polyethylene resists corrosion, a large filled tank can expand under water pressure. The external steel structure supports the plastic body, protects it from impact, and helps maintain its cylindrical shape. The curved ribs are aligned with vertical steel members and joined by skilled welders. Each connection must remain square and accurately spaced so the completed frame fits tightly around the molded tank. Workers alternate welding positions to limit heat distortion. Grinding removes sharp projections that could later damage the polyethylene body or prevent the protective panels from sitting flat. The finished panels are lifted and wrapped around the orange polyethylene tank. Workers align their edges with the vertical frame and reinforcement bands. Fasteners secure the jacket without placing excessive pressure on the inner vessel. Accurate panel positioning keeps the exterior round and prevents gaps where water, dirt, or moisture could collect between the steel covering and plastic tank. The upper supports, access opening, ladder, and external fittings receive their final alignment and fastening checks. Workers inspect the steel jacket, welded frame, and plastic connections before the tank leaves the workshop. Through controlled rotational molding, powerful heating, precision steel fabrication, and skilled assembly, polyethylene powder has become a durable, large-capacity water storage system. A massive FRP storage tank begins on a smooth, release-coated mold table. Workers prepare a thermosetting resin and spread it evenly across the surface. Sheets of fiberglass mat are carefully laid over the wet resin. This first laminate becomes the tank's corrosion-resistant inner liner. Complete saturation is essential, because dry fibers or trapped air could create weak points and allow stored chemicals to penetrate the wall. The cured fiberglass panels remain flexible enough to be lifted and curved into the initial cylindrical tank body. Workers guide the large sheet carefully while checking its diameter and edge alignment. The meeting edges are trimmed with abrasive tools before temporary supports hold the cylinder in shape. Accurate curvature prevents flat areas and ensures the later reinforcement layers remain evenly distributed around the complete circumference. Long strips of fiberglass reinforcement are prepared separately on a flat working surface. Resin is brushed across each strip before the material is lifted into position. Workers laminate these strips over the longitudinal joint inside the tank. The overlapping fibers permanently connect the panel edges. Rollers compress the seam and remove trapped air, creating a continuous wall rather than a weak mechanical connection. Continuous glass fiber rovings are guided through a resin bath and onto the rotating tank body. The winding machine maintains controlled fiber tension while the cylinder turns at a steady speed. Each layer is placed at a calculated angle. Circumferential fibers resist outward pressure, while angled layers improve stiffness and distribute loads along the tank's length without adding the weight of a solid wall. Filament winding continues until the shell reaches its designed structural thickness. Workers monitor the resin content and fiber placement as the enormous cylinder rotates. Additional fiberglass mat and resin are applied to selected areas by hand. These local reinforcements strengthen the ends, seams, and future fitting locations. Uniform rolling prevents resin-rich pockets and ensures the glass fibers carry the mechanical load effectively. Technicians mark the exact positions of the manway and pipe connections before drilling a circular pattern of bolt holes. The opening is trimmed carefully to avoid damaging the surrounding laminate. A heavy flange plate is then positioned against the reinforced wall. Accurate hole spacing and a flat sealing surface are essential because uneven bolts could concentrate force, damage the fiberglass, or allow stored liquid to leak. Workers install the flange bolts, sealing components, and internal reinforcement around each opening. Every fastener is tightened gradually and evenly so the pressure spreads across the complete joint. The tank interior is inspected for exposed fibers, incomplete seams, or sharp edges. Testing and final surface preparation confirm that the laminate remains watertight before the protective exterior coating is applied. A crane then lifts the enormous vessel into position. Through resin chemistry, fiberglass lamination, filament winding, skilled fabrication, and precise assembly, simple glass fibers have become a durable industrial storage tank. A precision aluminum bottle begins with seamless metal tubing selected for its low weight, corrosion resistance, and ability to withstand repeated forming without splitting. Each tube is mounted horizontally against a rotating mandrel, while hardened forming rollers work around one end. The rollers gradually curl and reduce the edge without applying one sudden impact. This initial profile prepares the lower opening for later closure. Accurate rotation keeps the wall concentric, preventing one side from becoming thinner or more heavily deformed than the other. The prepared blanks enter a powerful hydraulic forming station. Heavy dies compress and calibrate the aluminum, while coolant reduces friction and carries away heat. The operation is completed through controlled pressure rather than one aggressive stroke. Aluminum becomes harder as it is deformed, so gradual forming limits cracking, deep scratches, and excessive thinning around the newly shaped section. The bottles move through additional dies, with each machine making the shoulder narrower and the neck longer. Operators position every blank carefully before the powerful press descends. Progressive necking preserves a uniform wall thickness, while creating the smooth transition between the wide body and narrow mouth. Poor alignment would produce an uneven shoulder and an off-center opening. Rotary forming tools refine the bottle mouth and create the raised rings required around the neck. These repeated grooves strengthen the narrow section and prepare it for the closure system. Precise geometry is important because the cap must later tighten smoothly and seal evenly around the complete circumference. Additional presses and rotary tools complete the neck profile and calibrate its final dimensions. Bottles are arranged in rows while operators check each opening visually. The lower end is then mounted on a machining fixture. Cutting tools remove excess aluminum and create a clean, accurately sized recess. The resulting chips are collected so the valuable metal can be recycled. Circular aluminum-based discs are placed into the prepared lower openings. Powerful vertical presses force each disc into the machined recess and lock the surrounding metal tightly around it. A second forming stage strengthens and seals the connection. Uniform pressure is essential because an incomplete joint could allow liquid to escape, while excessive force might deform the thin bottle wall or damage the finished body. After final cleaning, the bottles are protected in plastic packaging. Precise cutting, progressive necking, powerful pressing, and skilled inspection have transformed simple aluminum tubes into durable, reusable containers. From precision glass reactors and aluminum bottles to massive storage tanks and a handmade wooden boat, every process combines powerful machinery with remarkable human skill. Which one impressed you most? Comment below, like the video, and subscribe to KenTT Machine for more amazing factory processes.